All right. Welcome. Today we're going to talk about lecture number 10, Deadlocks, first part. And this is again, along the way of the past couple of lectures in the synchronization. So last session we talked about semaphores a little bit more, and then we covered a few examples of problems of the synchronization: bounded buffer problem, readers and writers problem, and dining philosophers problem. And then we also learned about monitors and condition variables. You're going to use them probably in your Pintos as well. And then as an example, we also went over the sleeping barber problem. Okay? Is there any questions in any of those? No? All right. So, I also asked that you finalize the groups on AutoGrader. Again, do that because your design doc due date is tomorrow night. There is no extension. And continue with your implementation. To be honest, I don't see many questions related to your project on Piazza. That either means that you're all going, well with no question in project, which is good, but less probable. Or you're not making, progress so far that you're not actually going to those issues, which then that's bad news, right? So if that's the second case, try to, again, speed up a little bit. There is 2 weeks after this due date for your project number 1. And again, the sooner you get to the issues, the more time and more interactive you can be to TAs. They can answer your questions on Piazza, and then you don't have to just keep trying because there's half an hour before an answer comes, right? Just speed up. Okay. So today we're going to talk about deadlocks. First we're going to characterize them a little bit, and then we're going to talk about resource allocation graph, and then we're going to talk about handling deadlocks partially, and then the rest we'll talk about in the next session. All right? So as we saw last session, deadlock is when there are a few processes that each is waiting for the other one because they're holding a resource. So and then there might be other processes, but the set of the processes that each is waiting for the other one in the set, which is also waiting for another process in the set, then all of these will be in a deadlocked state. Okay? So, as an example, we have a system that has two disk drives. For example, let's say one process wants to read a file from this one and then write to the other one, and vice versa. The other one wants to read from this one and then write to the other one. All right? So, if P1 and P2 each hold one disk drive for reading, and then they're waiting to get access to the other one, and we're assuming this is they're waiting for this, they can't share them, and then they're in a process in a state of deadlock. Okay. So another example is, as we saw last session, if process 0 and 1 are here, one is waiting on semaphore A, and then if it's granted A, and then wait for B, while the other one at the same time gets B and then wants to wait for A, then they will indefinitely wait for each other, and then they will be in a deadlocked state. All right? So the next example is bridge crossing. So let's take a look here, and then there's a bridge in in the street, and then traffic only in one direction. That's kind of like how your programs work, line after line. You don't jump back in the lines, right? And then each section of a bridge can be viewed as a resource. So once this car grants this part of the bridge, then they have to take this one. Vice versa. If they take this side first, then they have to wait for this side, right? So in this case, this is exactly like the previous example of semaphores 0 and 1, A and B, and this is process 0 and 1. So they have both granted one and then waiting for the other one, which is held by the other one process. So what is the solution to this example? Can you guess? What is it if it ends up on the streets? What do you do? If you're in a parking lot or a bridge and then actually you head to a car, what do you do to solve this? You back up, right? So one way is to, if one of them backs up. But in the computer or operating system terms, it's like preempting that resource and then rolling back the process, right? Because the process has already made progress up to this point. Now, if the operating system, for example, wants to release that, then they might have to roll back, instructions or. But sometimes there are other cars waiting behind you, right? And it's not that easy, because this means that then not only you have to back up, then there are other cars or let's say processes, that have to back up and restart all over again, right? So resolving deadlocks is not that trivial or easy. So it's one way is to basically avoid them. So a deadlock, in terms of like the definition, is when two or more processes are waiting indefinitely for an event that can be caused by only one of the waiting processes, right? Again, another example, around the block this time, okay? So, and this is like different than the definition of starvation. So, starvation is only indefinite blocking. When a process is starved, it means it's not given the resource that it's waiting for. The reason, it doesn't matter. It's being, there might be other processes making progress while this process is, starving. For example, in terms of a, low priority when it does not get scheduled, right? It's not a deadlock, but it's starving. It can also be waiting for a semaphore or a condition that it's not going to happen or may never happen. Again, it may, block indefinitely, but it's not a deadlock because other processes are making progress and, there's no set of processes waiting for each other. There's just like one process waiting for a resource. Okay? So, when deadlock happens, there is the 4 conditions, all of which should hold. It's not like either, all of it. So, the first one is mutual exclusion. We have learned about it last session. So can you tell me, what is it? Yeah. Yes, when you actually have a resource that is non-shareable, right? It's on the screen. So, when you have a resource that can be shareable, it doesn't hold. Actually, we're going to see an example. But when you have a mutual exclusion, that there are other processes that they have to like fight for the resource, that is the requirement for a deadlock. All right. So next one is hold and wait, meaning if the processes hold at least one resource while waiting for the other one, right? So if a process, they may access many resources, but they don't wait for the other one before releasing the other one, right? That doesn't happen. They have to acquire a resource and hold it and then be blocked for another resource. That is, again, a requirement for deadlock. So the third one is no preemption. If the resource allocation is not implemented in any way that the processes can be preempted. Meaning, you remember in the scheduling terms, when we were like talking about scheduling, preemption was that the OS forcibly takes the CPU, take the resource away from the process. So that is an example of a resource, CPU. But in general concept, basically, preemption or no preemption is when you are not forcibly taken away from your resource, but you have to just like finish your task and then voluntarily release it. So if this holds, then there may be a deadlock for that resource. Okay. So again, if you remember, like in terms of CPU, we cannot think of it because the processes actually don't run if they're blocked. But if it is implemented in a way that the resource can be preempted, then the deadlock won't happen, right? Because that preemption takes away the resource from them, and then I'm not basically holding it anymore, right? So this again is one other requirement for a deadlock to happen. So the fourth one is a circular wait, which is somewhat when you think about the deadline or that like cars around the block waiting for another, like one waiting for the other, right? This is the official definition. When there is a set of processes, let's say from P0 to Pn, and P0 is waiting for P1, P1 is waiting for P2, and so on and so forth. And then in last, Pn minus 1 is waiting for Pn, and then finally Pn is waiting for P0. If you can mathematically show this in a circular, diagram, then it is, again, a requirement for a deadlock. All right? So take a moment and, look at them. If you have any question about any of them, just shoot. Yes?
For example, let's say you wanted to show the exam, right? For example, this is a deadlock. Would you like to draw something?
Come again?
Would you like to draw the picture of that?
Yes, that is the next part of the lecture, resource allocation graph. All right, so this is how you can basically draw the situation and then find out, for example, if there is a deadlock or not. So for the resource allocation graph, we have basically 4 parts. One is the process, we show it with a circle. Then the resource, which we show with a square and with the number of instances. For example, if it's a semaphore, initialize with number 4, which means there can be 4 of these resources allocated to processes without any waiting, then you draw it with like 4 instances, right? And then there is a request edge, which is shown by an arrow from the process to the resource, which means the process is requesting that resource. And there is an assignment edge. So when PI is holding an instance of RJ, it has been assigned, that resource is assigned to the process. Okay? So sometimes these two might be, confusing. Just make sure one of them is just request when the process is reaching out to them and is waiting for them. The other one is kind of like referring to the past, which that resource has been already allocated to the process, right? So let's see. This is an example of let's see if we can think about or draw a resource allocation graph for this situation. When we have like semaphore A and B, classic example of a deadlock, right? So I'm gonna just turn it off. And no. So P0, that's enough. And P1, wait A, wait B, wait B, wait A. So B and A, remember they are semaphores. I saw a question on Piazza. It doesn't matter which thread or process, but you wait on a semaphore. The semaphore might be defined in part of a thread, but all right. So remember, processes were with circles. So I have a circle here with P0. I have a process here with P1. And then semaphores or resources were shown in a square. So we have 2, A and B. One is A. How many resources are in it? 1. It was mentioned in the question that they're initialized to 1. And then 1, which is B, again with 1. So what will be the resource allocation for this? So they're waiting for A. What was the request edge? This side, right? And then waiting for B, which is like this. And then this is waiting for A and waiting for B. Is that correct? No. Right? I haven't told exactly how to draw a resource allocation graph, but we're going to see it in a slide. But think of how you have learned or just thought, if you haven't read the next slides, why this is wrong. Yes?
You only could one at a time?
Yeah. You wait one at a time. You can't. They're not waiting for A and B. They're waiting for A and B. So if process 0 is waiting for B, what does it mean? If process 0 is waiting for B, it means it has reached this line. What does that mean? What's that? It has already passed the weight A. So it has been allocated A. So if P0 reaches this line, it has been allocated A. The same goes with B. If B is waiting for B, that means it has not reached this part, so basically this is not there. So the resource allocation graph is not for a program or a set of programs. It's for a state, an exact state in an instance of execution. So this basically can have many possible allocation graphs in time, depending on what is the state of each process at the moment. Yes?
So when an arrow is pointing from the resource to the process, that means
it has been already allocated, yes. Right? So if you want to basically draw this graph, you have to understand what is the state. What is the process's state? So they start with this. We have one instance of the semaphores, and the processes, they haven't done anything yet. So then we can go through the possible execution flow, right? So as an example, let's see. They are symmetric. So let's say first this line runs. Weight A runs. Is there any problem with this request? No. So this will be granted. Now let's say weight B executes, but not finishes yet. So when P1 waits for B, it has a request edge. But let's say it has not been finished and not granted and preempted by the scheduler, and P0 is again put back on the CPU. So then it requests weight B. So P0 now also requests B. Is there any problem yet? No, they're requesting. So what? So now it depends. If P0 keeps running, continues to the actually finishing B, and then B gets allocated to A. At this point, P0 is here. P1 is still waiting for B. So what is the state at now? P0 has A, P0 has B, P1 is waiting for B. That's it. Is there any problem in this one? Yes.
Shouldn't the arrow be the other way? If B is allocated to P1?
B is not allocated to P1. It's still waiting. B is allocated to P0.
Okay.
Right? They were both waiting on P0. They were both waiting on B. So it's either of them would get the resource, right? It depends on the scheduling, right? So in this case, in this example, I'm just like continuing P0, so then the resource B gets allocated to P0, and in this case, both of the resources are held by P0, and then basically it keeps running, it goes into its critical section. Right? And then, for example, it releases them, right? Release, let's say it first releases A, which is not good, but let's say it's doing it like that way. And then releasing B. So once it reaches this line, once it passes this line, let's say I'm removing this. Once it passes the release A, the allocation edge or assignment edge is just like gone. Now this is the resource allocation graph for this state. Next line. B is still waiting because it's waiting for a resource that has been allocated to another process. So B doesn't get allocated. P1 does not get scheduled. Alright? So now A runs another line and releases B, which means this resource also gets freed. Again, this resource allocation graph is for this state. Now, operating system actually can take a look at the processes waiting for B since it has been freed, and then says, okay, P1 is waiting for B, B is now freed, okay, now I'm allocating B to P1, and then basically wake process 1 up. So now it's in between these two lines. So now P0 can continue. We don't care at this point. Now P1 runs the next line, waiting for A, which means a resource or a request edge to resource A. This is a resource allocation for this exact line. Then, again, because the request can be handled by the operating system, no one is holding A, then A will be allocated to B as to process 1. Sorry for my mistakes. Then A gets allocated to P1. P1 executes next line. It can now continue running and then releasing them at some point, you wipe them. So resource allocation is for the state. In this example, we saw it. There was no deadlock. The deadlock, remember, are not guaranteed. When we talk that there is these conditions and whatever, these impose basically a chance of deadlock, which now you might have already thought of. So if they start from here, P0 runs this, P1 runs this, P0 gets allocated with A, and then P1 gets allocated with B, still no deadlock, right? Then this goes to the next line and waits for B with a request edge. And then P1 goes to the next line, and then it has to block because B is held by another process, right? So P0 now has to block. Now P1 also goes to the next line now, and then waits for A. Now when P1 waits for resource A, again, this has to wait because there is no more resource A. Remember the instances. This is also important when you're drawing the instance to have the exact number. So in this case, because there's only one, that is allocated, so this has to go to sleep. And now we have a deadlock because we have P0 and P1, each of which is waiting for the other one. Yes? Well, in this case, they haven't. There's no preemption, and they voluntarily have not released them. Yes?
How can your computer actually tell when there's a deadlock?
What's that?
How can you tell when there's a deadlock?
How can we tell if there's a deadlock? Exactly, that's the next one. So in the resource allocation graph, let me bring this down. Resource allocation graph allows you to find if the current state is a deadlock. So in this example, again, we're dealing with multiple instances, right? Let's take a look first. So process 1 is waiting for resource 1 while holding one instance of resource 2. Process 2 is holding another instance of R2 and also has been already allocated the instance of R1 and is now waiting for R3. And then R3 is being allocated to P3. And we have also a bunch of R4, which no one cares, right? So this is just an, again, instance. This is not a deadlock yet. So it's just like an instance that, when you're dealing with the instances, you can actually start drawing the arrow to the instance so it makes it more clear, all right? So when you draw a resource allocation graph, if there is no cycle, there is no deadlock. That cycle basically shows that circular wait, right? Because each direction from a process to a resource shows a request. And then basically, if you're requesting a resource, we said that deadlock can happen if that resource has been allocated to another process. So that means an arrow from that resource to another process. And again, if that process is waiting for another resource, if they're progressing, there's no deadlock, right? We talked about a set of process each waiting for a resource which is held by another. So that is a circular, arrows between a process, a resource, a process, a resource, and a process, a resource. If there is no cycle, there is no deadlock. What if there is a cycle? There's not a deadlock yet, but there may, right? So it depends. What does it depend on? Yes.
If there's preemption or not?
If there is preemption or not. If there is preemption or operating system can force release the resources, then basically that is one way to avoid or resolve the deadlocks, yes. But considering we don't have preemption, does a cycle in the resource allocation graph lead to a deadlock?
There's still extra resources.
It depends on the number of resources, right? If let's see, if there is only one instance per resource, then there is a deadlock, because that's the simple case that we have thought of. When you think of a resource, a physical resource, it's just like, okay, this one is held by me, so it's not there anymore. So whoever that wants to wait for it has to wait for me, right? So this is very important. If there is one instance, waiting for that resource means waiting for the process holding that instance. There's no other way. But if there are multiple instances of a resource, that doesn't necessarily mean, right? So we're going to see in the next example, but the rough, if you want to just think of it, is that if you're waiting on a resource, and this resource is held by many processes, because it had many instances, you're not necessarily waiting for one of them. You're waiting for any of them. Okay? So that will make it easier, basically, for that resource to be released. Because any of these processes, if they release that resource, then you can be granted. So let's see. In this example that we're showing, we have a circular, we don't have actually any cycle, sorry. In this example, we don't have any cycle. This is not here, this here, this here. There's no cycle here, there's no cycle nowhere. So actually there's no possibility or chance of deadlock at this state, right? So how about this? Now if the P3 makes a request to R2, is it a deadlock or not? So we first think we have to look for the cycle. Starting from here, for example, this, yes. So there is a cycle. So there may be a chance. Now let's take a look. This process is waiting for this, which is held by this, which is waiting for this, which is held by this, which is requesting this. Now there are multiple instances here, so let's take a look. This resource is held by two processes. Both of them are in the set. Both of them are waiting. So in this case, the process 1, 2, and 3 are in a deadlock state, because each of them is waiting for a resource that can only be released by another one of these processes. Okay? Does that make sense? This is the crucial thing. When all of the processes are waiting for some resource, those resources are held only by the processes of the set. So let's take a look at the next example. So here we have another cycle, this one. And at this instant, both of these resources have been, allocated. Both of these instances also have been allocated. So there is no resource left. And P1 and P3 are in the cycle. So P1 and P3 are in the set, right? But they're waiting, either of them are waiting for a resource that is not necessarily waiting for the other process in the set. So in this example, P1 is waiting for R1. There is no R1 left. But R1 is not only held by P3, it is also held by P2. P2 is not waiting for anyone. It can finish its task, release this resource, then this resource can be granted to P1, and then everything goes clear. Or vice versa. P3 is waiting for R2. One of the instances of R2 is held by P1. But there's also P4 here held the other instance. This can start finish its critical section, release this instance, and then, continue. Now, you may say, okay, what if P4 doesn't release? Yes. We are assuming, remember, a non-zero speed of progress, right? You can have rogue programs. You can have, frozen processes. These are things that we're not talking about. But as a, general rule, if there's other instances held by other processes not involved in the set, then that is not a deadlock. All right? So What we learn is that a cycle is necessary for a deadlock, but it's not sufficient. It is sufficient if there's only one instance in all of the resources in the set, in the deadlock state. But it does not. It's not sufficient if there are multiple instances. Okay?
So,
yes.
If all the processes are waiting for a resource?
It is a deadlock if all the processes are waiting for a resource, and all those resources are waiting for the same processes.
For the same process?
Yes. I mean, they're basically held by one of the processes in the set. So by waiting, I mean they're waiting to be released by them.
Okay.
Right? In this example, see, P1, P2, and P3 are in the cycle, right? So when we think about the deadlock, we are considering only P1, P2, P3. If there is another P4 and P5, taking R4, we don't care. Now, what else are involved in this state? Is R4 involved in the deadlock state? No, because none of these processes are, holding or waiting for R4. Now, let's take a look at R1, R2, and R3. R1 and R3 and R2, all of them are depleted at this point. They're allocated to, other processes, and only to these processes. So there's no way that one instance of R2 can be released, back into the, state. In this example, it's the other way. So P1 and P3 are in the, set, and R1 and R2 are also involved, not any other resources, it's not even drawn. But R1 and R2 are not necessarily waiting just for P1 or P3. R2 is waiting for either P1 to release it, or another instance of R2 can be released by P4. Same goes with P1. Yes?
In the previous example, so let's say if one of the arrows was switched, so let's say from P1 to R1, if that's important,
Uh-huh.
would P1 still be in deadlock, or would it just be P2 and P3?
So first of all, in this case, you cannot reverse this arrow because R1 is one instance, so you can't have two arrows away from R1, allocating two of it. Let's say if we had two R1s, one of them was allocated to P2, the other one was allocated to P1, and then there was no deadlock because P1 had the resources that it wanted to, R1 and R2. So P1 is not waiting for anything. And then P2 with P3 actually had a cycle. Now let's take a look at that. So in this state, P2 and P3 are in this state. We don't care about R1 because that's not in the cycle. Although it is held by P2, but it is not in this cycle. So how about R3 and R2? R3 is held by P3, and P2 is waiting for that. So R3 is kind of, is waiting for P3 to release it. Right? So it's kind of, it doesn't help us. How about R2? In the case of R2, one of the instances are held by P2, one of the instances are held by P1, so there is no R1 left. That means P3 is waiting and blocked. But they are not in a deadlock because R2 has two instances. One of them is waiting for P2 to release it, but it may also be that P1 finishes its task, releases this one, and then P3 can be granted this one. Then P3 has the two resources that it wants. Then it finishes. Then it releases the R3. Then P2 will get allocated and then go on. So these are the chances in the future. When we talk about a deadlock state, that's a definite state. When we say there's no deadlock, that doesn't mean that it may not in the future happen. It may happen. But at this instance, they're not in a deadlock. Because once you're in a deadlock, there's no way out. The processes are just indefinitely blocked. Right? But if you do the opposite way, then at this point, there's no deadlock. There is a chance that, again, depending on the order of execution, if P1 runs completely and releases all its resources, then everything clears up. Okay? In case of the bridge, for example, I don't want to go back all the way to the slide, but if the cars are not actually waiting for each other, it's kind of like that. The car is there, so you can't move out, but maybe they have gone out, to get a chips or something, right? Maybe they come back and then they go, right? They're not waiting for you or the resource that you are holding. All right. So now in this example, this is an exercise. It is in the slides. If we finish the slides, which we may. We come back and then start drawing this. Otherwise, you, again, remember, there is no single instance of execution in this. Any of these processes can basically be at any of the, points of execution. Well, you cannot have a imaginary situation. You have to run them, from the start. You can't say, hey, okay, I assume that P0 is at this state, P1 is at this state, and P2 is at this state. Maybe that state is not reachable, right? But once you start running them one at a time, then the order of the scheduling can vary. So then at each instance you can draw a resource allocation. What's that? In this case, yes. All of them is just like one instance. Alright? So next is how we can handle deadlocks, or prevent them, or solve them, whatever. The first thing is ignore the problem altogether and pretend that deadlocks never occur in the system, and then, leave it to the programmers. Right? That's just like one idea for the operating system. And although it may seem funny, actually that is the way Linux or Windows work. Right? They don't do anything anyway. It's just like left to the programmers. So you can easily, that's why you may have like frozen, programs or something, because that has happened. Your program has not like handled its, execution flow or synchronization, and it's just like, blocked or deadlocked, whatever. Now, the other way is to use a protocol to prevent or avoid deadlocks before they happen, and then basically ensuring that the system will never enter a deadlock state. That is one way to do that. So, for example, one is deadlock prevention, meaning, you remember, for a deadlock to happen, we required we had 4 requirements. So if you basically provide a set of methods to ensure that at least one of those necessary conditions does not happen, then the deadlock can happen. Right? It can't happen. So that is the prevention. Now, deadlock avoidance is another way, which is similar but has like slight differences. We're going to talk about it in the next session. Also, another way is to allow the system to enter a deadlock state, detect it, and then recover from that deadlock state another way. So then we're going to talk about the deadlock detection and recovery again on Tuesday. All right? So today we're going to talk about deadlock prevention. Again, remember, deadlock has 4 necessary requirements to happen. All of them had to hold for a chance of deadlock. So if any of those are not held, there is no chance of deadlock. So let's see for each of them. So the first one was mutual exclusion, right? And mutual exclusion, if you remember, was for the resources who were limited, were not shareable. Either they were like, one instance, so one process could hold them and then not the other ones. The other one is multiple instances, but again, they're not like shareable in the, for everyone, for infinity, right? So, but this is not, but mutual exclusion holds for non-shareable resources. So an example is accessing read-only files. They do not require mutual exclusion, right? So there is no deadlock involved with a read-only file. How many other processes that want to access it? It can. There is no problem with that, right? So can you make all the files read-only? No, your system does not work, right? So the problem with this is the idea is okay, but it's not practical because mutual exclusions are inevitable. As we have seen, if you don't do them, there are other problems that can happen. So, how about the next one? Hold and wait. Remember, the hold and wait condition was for when one process was granted a resource, held it while waiting for the other one. So, can you kind of come with an idea or a method that prevent this from happening? How? For example, one idea is to require process to request and be allocated all its resources before it begins. If you want to prevent from a wait and hold situation, one idea is that you basically propose all the requests that you want. Now either you'll be granted or wait. But now while you're waiting, you're not holding anything else. And once you are granted, then you can go forward and not wait for anyone else. Okay? So this is one way. And then the other one is allow process to request resources only when the process has none. So you don't propose anything in the start, but once you start requesting something, I'll take a look. If you hold something, I don't give that one to you. I don't, I either force exit you or preempt you or something, right? So the hold and wait does not happen. An example is let's take a look. Let's take a moment and think of a process that wants to read from a DVD and then write it into a file and then print it. There was file involved here. So yeah. No. This is either. You can implement this method either way, and then we'll see what happens. So let's take a moment and think of a process that wants to read from files from a DVD, write them into memory, and then save it into a file or do some file sorting, whatever. This is an example from the book. And then basically after that, once it's done with its processing, then print them using a printer. So basically they want to acquire DVD, they want to acquire the disk drive, and they want to acquire the printer. So what happens if we want to basically use method A and then let the process run? Can anyone tell me? What does it mean? Require process to request and be allocated all its resources before it begins. So for this case, what does it mean? Yep. They would require the DVD if they want to write or do some file processing. They also want to get the disk drive, and they also need to request for the printer and not let anyone else use the printer in the meantime. So what does that mean? What does it end up? You tell me. If the process requests for the printer, DVD, and disk drive before it even starts, and then it has to allocate it has to be allocated all the resources all the way to the end. So what can go wrong? What is wrong with this? And the other processes are waiting for their resources, right? Unnecessarily. So one issue is that if it's holding the printer while it may actually need it in half an hour, then it will just prevent other processes from using the printer in half an hour. That's a low resource utilization. It's not good. And then the other thing is it may never get resources at all, because maybe in the meantime other processes are using disk at the same time. Maybe another process wants to do something with the DVD, maybe another one wants to print something, and it may never find a time to have all of them free at the same time. Right? And again, if you think of this example, it's not a undoable task. It just wants to read something and then print it. It's not like a complex task. Go ahead.
Yeah, so for this, you would have to disable preemption then, for sure.
We have not. I mean, it is a general concept, but yes, in this case, we're thinking that we're not preempting any process of its resources, right? So now, what happens if we allow process to request resources only when the process has none? So once it has the DVD, then we won't allow it to use the other one resources, right? So it basically can never run, right? So it's just it may lose it. Either it will has to starve or completely we close it, or in case of a preemption, it means when it is accessing DVD, it's fine. Once it asks to request for the printer, because it is holding the DVD, now the operating system may say, okay, I'm just gonna force release the DVD or disk drive, and then grant you the printer. But the process wants to make sure that no one else accesses those files so that these data are intact. Right? That was one of the examples of the mutual exclusion and holding a mutex lock, right? So if I have a process and I want to basically, I'm processing this file and I want to print it. In the meantime that I'm not done with printing yet, I don't want anyone else touching these, right? So I'm just want to acquire the printer while I'm holding this and then go ahead. So if this is forcibly preempted, I don't know, there's no guarantee that I don't lose my data. There's no guarantee that no one else messes up with this data. So it's basically with the functionality of the process. So preemption can happen in terms of the operating system. Yes, operating system can preempt something. But it's not always it's not going to work with the functionality of those processes. The problem is in the preemption. We're going to talk about in this one. So, how about the preemption? We talked about, we just made an example. So, if there is no preemption, then there may be a chance of deadlock. No preemption was one of the required conditions of a deadlock. So, what can we do to avoid it? Well, we can implement preemption. So, if a process that is holding some resources and requests another resource that cannot be immediately allocated to it, then that's the, hold and wait situation. So then, let's do this. Then all resources currently being held are released, and we're going to talk about the alternate, right? And then preempt them. So preempted resources are added to the list of resources for which the process is waiting, and then it will restart only when all of them granted. So let's take an example here. So the text is too much. I'm making an example here. So while I'm holding this, I'm doing something, and then now I want to copying them into this. So I ask the operating system that, okay, I also request this one. Now, because this might be, taken away by someone else, I might ask, okay, I need this. I'm waiting for this resource. So at this point, I am holding and waiting. So in this case, one way is for the operating system to be not generous and say, okay, now that you're waiting, why don't you wait for all of them? So give me this back, right? So now I don't have anything, and I'm waiting for this. At the same time, I have lost whatever I had, and I'm waiting for that at both of them. So the operating system will only restart. Restart means continue in this example. The execution once all of them are available. So in this case, again, the idea is that, okay, I'm not holding and waiting, so anyone that wants to access this in the meantime, this one, all right? I'm not holding it for anyone, so it's there, they can come and run. The slightly better version of this is that, okay, we don't preempt all your resources, on your request, but if you are waiting and another process wants your resource, then we preempt it. So, in this example, back to this. This one is held by someone else. I hold this one. I'm running. Now I want to wait for that. The operating system does not do anything in preemption yet. It says, okay, wait for it. Someone else is using. I'm holding and waiting. Now, if someone wants this, because I am holding it while waiting, the operating system says, oh, okay, now you're holding this, but someone wants it, sorry, you're out, right? So it forcibly preempts it, and then the same thing. I have to wait for both of them now, and I will only be allowed to execute once both of them are available, so the operating system grants me both, and then I can continue. So again, the idea is this solves the deadlock, which again, if you think of it, it does. But what's the problem with this one? Let's take someone new. If not, I'm coming back at you. Can you guess? Yeah. Exactly. Just like last example. You might, I was holding it for a reason. Maybe I needed, not anyone else. Maybe I needed that mutual exclusion. Maybe I am in my critical section. So if you, preempt it, what guarantees that, I'm gonna work? What if I, put some, files in this and I don't want this to be edited? I don't want anyone else to access it, right? So that's the problem with this. And actually it has been implemented, and we have talked about the preemption of the CPU, and CPU is a resource. But if you think of it, it's different because the CPU states are not shared. You have registers, and then all those registers are saved in the PCB, the process control block. So even though the CPU resource is forcibly preempted from each process, but the state of it is exactly saved in the PCB, and then no process can have access or basically overwrite each other's, states, registers, flags, whatever. So this is the difference between, for example, a CPU and a mutex. If I'm holding a mutex for a file or something, I don't want anyone else. So if you preempt it, the functionality is basically jeopardized, right? Anyway. So circular wait is the last condition. The fourth condition, which is basically we can impose a total ordering of all the resource types, and require that each process requests resources, for example, in an increasing order. This is a solution to the circular wait. You remember, the circular wait was for when a process is waiting for a resource, that resource is held by another process, that process is waiting for another resource, that resource is held by another process, and so on, and everyone is waiting for each other, right? Now, what we can do is that what causes this is that if you remember the dining philosopher problem, this is the exact thing. I was going for my right fork, then my left fork. And then the other philosopher, I considered myself as one of them. So the other one also wants to go for their right fork, and then their left. Chopsticks, right? So then the other one also wanted to go for their right chopstick, then their left. The problem was that this ended up with a deadlock because each of us would grab one and then wait for the left one. Now, if we have an ordering of the chopsticks and then decide, okay, not all of you can first go for your right and then left because they are ordered, and you only can request them in the increasing order, meaning if they're increasing in the left to right order, let's say from the right to left, because I've already discussed this. So that means, okay, this resource is 0, 1, 2, 3, 4, 5, right? So if I want to grab 2 chopsticks, I have to first grab 0, then get 1. The next person, they want 1 and 2. They have to first get 1 and then 2. The next one. All the 4 people can do this. The last person can't do this. Why? Because if the right hand is number 4, the left hand is number 0. They're not following the order. They're first requesting for the higher one. And this exactly one switch can solve the deadlock situation in the dining philosopher problem. If one of them is a left-handed and requests the left one, then there's no deadlock. There's not going to be a deadlock. Okay? So the situation talks about the ordering. Can we do that? What is the problem with that? Yep. So, because the operating system has not defined the resources, it does not know what is the order that will be, in the future used. So how do you impose those ordering? The other one is like, what happens if you now impose an order and then another process is now requesting out of order? So what do you do with it? Do you forcibly preempt them? Do you close them? What do you do? Because you remember, that doesn't necessarily end up in a deadlock. It may end up in a deadlock. So if there is any out of order request and the OS is just like, killing processes, that's basically, it's too much of a overkill. Literally. And then what if order changes? So the order is imposed, again, what if the order is like dynamic? So what if a process calculates the order and assumes that, okay, this is, has to be requested before this, so I request this first, and then this. So the process actually wants to follow the order. But what if the other process calculates it based on, a different criteria, and then they decide that, okay, I should request this one, and then the same thing basically happens. So this example is basically shows this. So one thing that some operating systems, I think, do based on the execution they put them in order. So they don't have any order for them, but once a process requests this resource, the operating system allocates a number to it and say, okay, this is 0. And then another resource is taken, then that resource has been taken after this one, so the operating system thinks, okay, so that should be after this one, so I put the 1, 2, 3, 4, and then now if a process requests in a reverse order, then at least it may detect it. And I think in the book example, it says, like, I think BSD in Unix, I think, it warns that say, okay, all the resources of these processes, this is the order that they have requested. Now there's a process that requesting, out of order. So at least a warning is there, so you can think of, okay, is this, part of my fault as a programmer, or, what has happened? All right? So back to the same exercise. We're gonna show it actually in a couple of minutes. Please, if you after the lecture you may leave, but we want to continue. But this definitely you need to solve this exercise and then try to basically move some of these gets only in their own process. Don't move them across, but these D and E and B, change them a little bit, change these orders a little bit, or these, to avoid a possible deadlock. So, because, well, as you guessed, this exercise actually has a chance of deadlock, and we're going to actually see what happens, or in what situation that happens, and then you should try to, resolve it by trying to move them. All right? Any questions in these lecture slides first? Okay, so make sure you finalize your design document. The due date is tomorrow night, and then continue with the implementation. Okay, within the next couple of minutes, I'm going to continue running it on the, do this exercise on the board. Yes? Hold on a sec. What?
There's 3 processes, right?
Uh-huh.
Are you going to do one line from each process?
No, that's what it said. It totally depends on the execution. It totally depends on the execution order. So you have to think and guess, and think, is there, and I'm going to solve it. So if you're not in, I would actually ask you to stay, and then I'm going to show you how to basically think if there is any chance of deadlock. All right? So let me hold this up. So it asks for P0, get A, then B, I'm just going to short it like this. P1 is going with D, E, and B, and then C, F, and D. P2. All right. Let's see if there is a chance of deadlock or not in this situation, right? So we have allocation, resource allocation graph. Remember, P0, P1, and P2. There are 3 processes. P0, P1, P2. There are 6 resources. A, B, C, each of which we have only, let's say, 1 instance. D, E, and F. So, process 0 is requesting A, B, and C. We don't know the direction of the edge yet, but we know that P0 wants at some point A, B, and C. It may be allocated this one waiting for this one, or vice versa. P1 is dealing with D, E, and B. D, E, and B. And the last one is with C, F, and D. So C, F, and D. So What do you see? Do you see any loop? A cycle should first be on a loop, then the directions, right? So do you see any loop here? P1 and P2. What is the loop? Tell me, which resource? I should move from here to a resource, right? Well, this is not going to go away. So either that D or C. Which one?
I thought it was through D, but I can't see the line.
Okay, let's see. From P2, let's move on to D. Where should we go? P1. If we go down to E, there's no way out. So let's go to B. Now from B, we go to P0. Again, down to A, it's dead end. So then back to C, then to P2. So there is a loop. Not a cycle yet. Now, what is the order? So let's see one more time. I'll wipe the other one for now. So this is not there, this is not there, and this is not there, right? So we have a loop like this. So we can move these a little bit like that and make it a nicer loop, but I'm just going to leave it as is. So P0 in this loop, what is the order of execution between B and C? If it wants to be part of the loop, it has to be granted B and then waiting for C. Because if P0 is waiting for B, it means that it's at this line. That means it even has not requested C. Yes?
I think the line's a bit larger.
Yes, I want it to be faint so I can now draw a little bit thicker on it. So I'm sorry if you still can't see him, but so let's see. So in order for P0 to have a connection to B and C at the same time so that they actually show in the loop, it has to be not only in this line, which is, as an example, A should be allocated and then requesting to B. That is not going to be enough because at that point, this request is not even there. In order to have both of them, P0 should be at this line, get C. So it has already been allocated A and B and is now waiting for C. So you can see from here, here. So C should be allocated to P2 if we want a directional cycle. So P2 should be allocated C. How about F? Again, if we are at this point, then P2 will not show anything to D, right? Because it will show a request to F and nothing to D. We don't want that because that doesn't make it a loop. So F has been already allocated to P2, and then P2 is actually at this line. It's requesting D. And then D should be allocated to P1. That is for sure. How about the next one? If P1 wants to finish the loop, it has to make a request to B. So it cannot be at this line, but it should be at this line. Again, granted E and waiting for B. So if they run, in this situation, all of them granted the first two resources, waiting for the third one, then P1 is waiting for resource B, which is held by P0, which is requesting C, which is held by P2, which is requesting D, which is held by P1. And we have the cycle. Now, the cycle is there. Remember, if the resources are single instances, in this case, then the deadlock is there. If there was more than one instance of each semaphore, for example, then you have to double check with other processes if they're part of the deadlock set or not. Okay? So now, remember, as I said, you can't just imagine if this state is reachable. You have to basically run. Can this state reach? Now we know at least where we should end, right? So we can simulate the scheduling order. Let's see. I'm going to do it a little bit quick. So they start all at this state. Let's see. If process 0 requests A, it requests A. There is no problem. It will get granted, so it will be allocated. Then it requests for B. Again, there is no problem at this point, so then it will be granted. Then it requests for C. There is no problem, but for our situation, we think that, okay, it's the scheduler now changes to another process. It's the same state stays. P1 requests D. There is no problem, so we can actually move forward. This gets allocated. P1 requests E. Again, there is no problem, so we can move forward, and we actually do, because we want to reach to the third line, which is requesting B. Now I request B, and then again, we assume that there, even though actually there is a problem here, so P1 has to wait. Okay, move on to the next process. Process 2 requests C. The other process is requesting it, but it hasn't been allocated, so we can move forward another line and allocate C to P2. Now we move to the next line. We request F, and there is no problem with this. Again, we get allocated. We move forward to the next line, which we run this one requesting for D. I'm going to try it like this, right? So in this case, actually, I can also move this up if you want. Have not intersection and make it a little bit more clear, hopefully. So like this. Okay? So now the cycle is here. We actually reached it through running line by line, making sure that we could reach this state, and this state actually is a deadlock. So the answer to that exercise is yes. If you run them, at this order, in this order, up to this state, there is a chance that they get into this state, which is a deadlock state. Now your exercise is that, okay, can you change these orders anyway so that this does not happen? How you can show it? Again, on the paper, using first, shallow lines, try to make sure that there's no loop. If there is no loop, that cannot turn into a cycle, and then show that. All right? Yes? It could happen. It could happen that it doesn't, if each of them run in order completely, the deadlock does not happen. But there is a chance that they end up in this state. Alright? See you next session.